Let's talk VDML with KJR.
Hey, welcome to Let's Talk VDML Podcast. Today I'm your host, Kelvin Ross, and today I'm joined by Stan Potums and Joe Burton, who play pretty key roles in the data store and ML ops side of the projects that we do. Today's topic is discussing data stores. What is the importance of data stores to validation-driven machine learning? And what are the essential things that really make the success of any project developing ML models and making sure they're reliable, trustworthy, traceable? And so let's kick off. Maybe Stan. Can we maybe talk about a couple of projects that we've been using data stores for, particularly in the health space, and then we'll dive a bit deeper.
Yeah, sure thing. So I've mainly been looking at data store and doing a bunch of modeling with echocardiography data. Just to put a bit of context here, this is the image. It's a video that's been taken by a handheld device to look at the heart from different angles. And this data is then stored on the medical devices as a file type that's called the DICOM format. And that DICOM format is the raw data from a data science perspective, and that contains a header with a whole bunch of metadata, and then a section of the pixel data. So this is semi-structured in the way that there is the metadata, but then you have there's not much information of what you're actually looking at. So there's a lot of questions around which of these DICOMs would be useful for further processing. So a big part of this project is really storing the data and then really like unpacking it and trying to come up with rules to start creating a little bit more structure of this type of data.
Cool. Thanks, Dan. And Joe, you've been the lead on the TAWI project with all the ICU data. But today we're going to chat a bit about a sort of a subset of that data around the ECG data, which is the electrocardiogram data and the models we build from that. So maybe a bit of an overview of what's sort of in ICU data and sort of what is specific about ECG data compared to other data.
Yeah, sure. So at the TAWI, we had agreements with hospitals all across Queensland, and we pulled in their primary ICU database, and that's called MetaVision. So MetaVision is a structured SQL database run on SQL Server, and that contains sort of a variety of data points describing patient episodes. It's relatively in the grand scheme of things, it's relatively high frequency compared to the ward data, but we'll get onto the echo or electrocardiogram data in a second, which is much more high frequency. So the MetaVision data sort of collects a huge variety of data points describing a patient's stay in ICU. So any patient who's admitted to an ICU unit in Queensland will have data collected and stored in MetaVision, and that will describe sort of there'll be data points around the patient's condition, around their next of kin, the treating physicians, around allergies and these sorts of things. So basically any data point you'd need to find relative to a patient, you can find somewhere in MetaVision. So alongside that, in at least some of the ICU units in Queensland, they will be hooked up to an ECG monitor. So the the data off these ECG monitors is recorded at sort of varying frequencies. So we primarily interacted with GE Carescape, who was the provider, and the data that we were pulling off there was 240 hertz. So 240 data points per second were recorded. So this data is actually summarized in Metavision. So Metavision has a heart rate, I believe, signal or data point, and that is, I believe, like a minutely average or something like that of that ECG data. But we wanted to pull off the actual raw ECG feed itself and pull that into our data platform. So those I guess the challenges sort of associated with pulling that data into the platform are quite different from what we found when we pulled Metavision data into the platform, being sort of much higher frequency and things like that. The volume of data was significantly higher, and we needed to develop alternative strategies to address those challenges and make sure that data was smoothly ingested into the platform. So I'm sure we'll touch on those a little bit more as we go on.
Yeah. So it's interesting the different kinds of data you guys are talking about. That on one side there's the structured medical record data. So you talked about Metavision. Stan, on your side, you've got like the reporting database, right? What the radiologist finds in the results of the imaging work. But then the core of the models that we've been working on is that low-level data. So that ECG data, the electrocardiogram, and I think Americans call it EKG, which I don't know where the K comes from, but it's easy to get confused with an echocardiogram, which is what you're talking about, Stan, which is an ultrasound, which is a video. So one is like a 1D graph, and there might be many signals representing different leads, but we're talking about one-dimensional sort of time series. We often call them waveforms and things like that, versus a video, which is a 2D or actually a 2D image, but with time as a third dimension. So when we look at the machine learning models that we build off those things, Stan, what's the kind of machine learning models that we're trying to build from the echoes, from the video data?
Yep. Yeah, we looked at a few modalities there. There's definitely, ultimately, we're trying to often predict, I guess, volumes of certain sections of the heart was one project. But to get to that point, we gotta first know what we're looking at, which, like I mentioned at the start, each of the videos might be looking at a different angle, might be zoomed in on certain sections of the heart. So before we can even reliably predict something in this imagery, we want to do some classification first. So yeah, a big application is looking at view classification. Are we looking at a typical 4-chamber or 3-chamber video? What's the quality of this video? Is it useful or not? So for these purposes, we've been looking at classification models. Once we have certain views and qualities filtered out, we could then do more downstream tasks like image segmentation, where we will just classify all the pixels within a certain section of that view, and that could then give us some more information about volume or I guess relative volume of what the heart's pumping. So there's definitely the main focuses, I guess, the segmentation and classification.
Yeah.
Echocardiography.
And I guess people are pretty used to image classification and image segmentation and how that might be used in a video. But Joe, with the 1D data, we often call it 1D, like a waveform. We're still doing classification and things like that as well, but it's a little bit different, isn't it, to the sort of image classification tasks that we do?
Yeah, absolutely. I guess it's perhaps more of a traditional classification task with a single sort of vector of numbers that you're then looking to classify in some cases. So the ones I remember in particular were peak detection. So if you can imagine an ECG waveform, has peaks and valleys. So the tip of the peak is known as the R peak. So the first project I believe we worked on was trying to develop a model to automatically identify R peaks within that signal. And then once we'd had a fair go at that, we moved on to arrhythmia detection. So trying to detect sort of arrhythmic signals. So when a heart's perhaps beating at a out of a consistent pattern. So with a beat out of sync every now and then.
Yep, perfect. So in the projects that we do, like most projects, we rarely start necessarily trying to build everything ourselves, right? So I think both these projects involved a bit of transfer learning. So I think we use the Stanford model for a lot of the arrhythmia detection. Again, a 1D ConvNet, and equally, other classification, we probably use ConvNets for view classification, things like that on the video and 2D stuff as well, Stan. But we equally had sort of standard models that we'd try to use, like we'd be trying to transfer learn from other models. Is that right? Or
yeah, that was the case for some of my projects for sure. So for the view classification, there was a few models out there. Interestingly, it's not just plug and play. Often we found that just applying these models to our data wouldn't really work. And then there was two reasons for that. One would be the image pre-processing. So a lot of these models were trained on data that was pre-processed in a certain way. And this wasn't always communicated or documented very well. So that was a bit of a challenge at times. And in the other case, it's just a matter of distribution shift. So and this means that the data the model was trained on looks just different in several ways to the data we're actually adding now, and that's just a change in the way pixels are organized could really throw off, confuse a model. And then there was the other thing that in view classification, each, I guess, paper or each cardiologist has a different taxonomy like this. So some will have 23 views, some will go down to 40-ish views, and then some of the models would have grouped a bunch of views into 8, narrowed it down to 8 views, etc., etc. There's a lot of mapping required to actually get some value out of these pre-trained models.
right. So how would you sort of build that up? Would you take the existing pre-trained models and then run that against our data and see what the results were and then use that? Is that pretty much the process you were using?
Yeah, that's it. So I try to get a bit of a test set going first. So you create some data you expect it to be seen. So you want to have your test data kind of matching the expected production data. And that's going to serve as a bit of a benchmarking set for how well these models work and how well the pre-processing, I guess, of that imagery will work. So the test data we then had labeled by some of the cardiologists we work with. So we have that ground truth there. And then it really enables you to quickly run a whole bunch of different models and, like I said, different pre-processing pipelines, if you will, to just test on these test images and see how useful something will be, or how much of a stretch it would be to actually get some value out of these available models.
Yeah, so most of this machine learning, as we say in VDML, is quite data centric, right? So how important then is that sort of organization of the data and the labels to this process?
Yeah, happy to take this one. Yeah, that is quite important. So I see the whole data set versioning on a whole bunch of different levels. And I'll just break it down a little bit. So before we even start labeling, we will come up with a bit of a guide for labels. We have to agree what the ground truth is, right? I mentioned the 43 versus 23 classes. So you want to come up with something you agree with the client. And once you have narrowed that down, you'll start defining each of these classes. How do I know that I should label this image or this frame as this class? So you write all of that down and you start labeling using that guide. Now, you iterate a few times, you figure out that certain classes underperform, so you decide to merge classes. So you decide to instruct the labelers to do something different than they originally did. And now you'll have two types of labeled data. So you might have one image that was labeled A in version 1 of the label guide, and then the same image could be labeled B in this new version of the label guide. And if you don't keep track of those and you just mix up things, you'll start seeing weird things, your model being confused for no apparent reason. But if you then can actually, I guess, you can start debugging by almost looking at, this image was actually labeled according to label guide version 1. This is why I'm seeing this confusion here in the predictions. So that's a place where it's really important to keep that versioning. But then also, if I'm going to report the model is doing this well, and then someone else comes and runs it on a different test set that they got from me a few weeks earlier, they might get different results. So how do we know what we're actually talking about? If I'm saying my model is doing this well, how can we let other people validate, I guess, what we're saying is true? So I think that versioning comes in handy there as well, like in these test sets.
So this data store, and typically there's many people in the team that are contributing to the data store, right? But the data store is that central bit for recording not only the input data, but then the labels and the provenance of the labels, the metadata, other labeling information, right? That's all of that really needs to be traced quite well, so you always know where you are in that development path. Joe, maybe let's go back to the start of that process. So the first stage is inputting the raw data, but in both of these contexts, we're pulling in real medical data, right? And it's linked data where there's potentially identifiable information, things like that. So what are some of the processes in sort of the back end, that data store management, that are critical for managing that data? Because we just don't want to let PII information float around to the entire team, do we?
No, absolutely not. And I guess so preventing access to personal information was one of the most critical things we were doing at Datawi. That's one of the most significant challenges in sort of exposing that data to consumers of it. So I guess there are a couple different pieces to how we attempted that. So I guess the data governance model being one, and just a straight up de-identification process as well, sitting alongside that. So for de-identification, we were aiming to strip or at least mask the personally identifiable information in that data. So once that data has been stripped out or masked, we can then expose that freely or much more freely than before to consumers of that data. So there are generally a few different strategies you'll use to mask or remove fields. Like for example, some fields, if you deem that the value derived from that field is minimal, or potentially the risk of exposing that field to a consumer outweighs the benefit of doing that, you might just strip the field out entirely. So you'll just completely remove this from the de-identified data set, and that data point is just no longer available in that data. So obviously, if we did that with every field, we wouldn't have any data to share with the consumers at all. So we need other strategies for transforming some of these fields to actually make sure that the data is still available and usable. So some fields all fields would get transformed in some way. So there are generally sort of two ways we do that. The first just being to hash a particular value. So if you had a patient identifier, you would simply generate a hash of some sort. You would join in a salt to make sure that the hash isn't a direct output of the input, and then the resulting field then just becomes a sort of a jumbled string of characters that is, in terms of re-identifying the patient, it's meaningless because it's no longer tied to the identity of the individual. So obviously the key point there is that you need to maintain the integrity or maintain integrity in the output database. So whenever the same patient identifier appears in the input data, we obviously have to have the same replaced or transformed value in the output data. Otherwise, the data would make no sense anymore. So that was one of the challenges. The other sort of the other transformation we did was processing date fields. So dates are and the dates when a patient was in an ICU unit is a very identifiable feature because it will obviously greatly narrow down the number of patients that the data could belong to. So we needed to find a way to mask date fields while still maintaining some usability of those date fields. So we would apply, or to do that, we'd apply a shift to the data. So each patient, in the same way we generate a sort of a text-based hash of an identifier, we generated a numeric value which was essentially also the output of a hash function, but for that became the shift that each patient's dates would then be shifted by. So each patient in the database would get a unique shift generated for them, and then all of the dates associated with that patient would then be shifted by that same amount. So the dates were no longer accurate, that they no longer represented the time the patient was actually in the ICU, but obviously because all of the dates or all of the data points associated with that patient have been shifted by the same shift, you still maintain time series order in the output data. So you can obviously still compare the patient's entry point to exit point. They'll still be in the ICU for the same number of days and things like that. You just can't identify the actual time that we were or that patient was in there. So yeah, the first step in sort of masking out that PII was to directly de-identify it. So in order to effectively share that data, you also need a data governance model in place, and we need to be able to limit who sees each of these different data sets. So once we've done the de-identification, we wouldn't actually delete or remove the original data. You would essentially maintain two different data sets, one being the raw data set and one being the de-identified one. So we then needed to come up with a strategy to make sure that we could share or provide access to each one of those data sets to specific groups of consumers based on their needs. So the access to the raw data set would be much more locked down than the de-identified one, but we did find that there were still use cases where access needed to be provided to the raw data for some reason. So we came up with a data governance model on AWS, so primarily using Glue as a data catalog, and then Lake Formation as the data governance tool, and we could then share that data with specific consumers and maintain and monitor access to what each consumer is given, and then also be able to monitor the number or the specific number of consumers who have been given access to a specific data set. So we could see the data sets a particular consumer had access to and the consumers that had been granted access to a particular data set. So that data governance model alongside the de-identification was the two key pieces in limiting access to that personally identifiable information.
Yeah. Yeah, and I guess that that process continued throughout, also through like the labeling activity. We'd often give them data to label, like ECGs, but again, we're sort of using data to select what patients to provide them, but they don't know who those patients are, right? They just get a task list of the data. So that labeler is not even getting to see a whole bunch of information. They're more focusing on the raw data, but the data scientist is typically sort of dividing up the training and validation data sets and things like that based on, separating patients, because we didn't want patients in the same training set as the test set. We wanted completely distinct patients and things like that, because we found that would sort of leak. You know, it's almost like the model might learn the patient, you know, in terms of what their sort of shape looks like, and know that something happens later on to them, which was an interesting challenge of validation, to go back to our provenance and check that the validity of how we built the model was correct. On your side, Stan, there are also some tricky bits of de-identification as well, right? Like, it wasn't just, you know, changing the fields in the metadata or the report, but you had to sort of deal with sort of information in the videos themselves, right?
Yeah, that's correct. So, yep, for the structured metadata, we were lucky to have, Joe's work there to capture all the cases there, but then the video always contains burnt in patient information as well. So we often find that the name of the patient is written or burnt in the pixel data on the top of the image throughout the whole video, and there might be other instances of PHI or PII. So obviously there was no way of dropping this information as such. And then the extra challenge was that each software version or manufacturer has a different positioning of all that PHI or the patient information, and also different types. So some may include just the name, some may include the location of where the device was in the hospital. There's a whole bunch of different types of information. And to solve that, it seemed like some low-hanging fruit to just use some OCR, optical character recognition models that would find where there was text in the image, or when I'm saying image, I mean the frames in the video, and then if there is text, feed it into a almost like a PHI classifier. Yep, this looks like PHI. So now we're gonna black out these pixels that contained this piece of information. So we tried a few of those models, but once again, probably some distribution shift, because they were not very reliable, I should say. So what we ended up doing, just to assure that no PHI was leaked, is coming up with a more rule-based system. So if we knew that this DICOM came from this manufacturer with this software version, etc., we knew the location would be in a fixed position. So it was then coming up with rules for each of the possible combinations to black out that information. And then you could still run an OCR tool at the end to just double check if no text information, which could likely contain PHI, has seeped through.
Cool. And I'll come back a bit more about that automation process. But so in addition to the target data we're working with, you know, the hospital data, we're also pulling data from other sort of research sources, right, to sort of like pre-trained models and things like that we could then transfer to our data sets. So we had to manage other people's data sets as well, so not just our own data sets. Is that right?
Yep, in my case, that was definitely a thing. So as mentioned, we used some models that were published, and those models often are published with data sets, and you can access those data sets, but they often also require you to sign certain agreements of what you can and cannot do with the data. So I think that was the first challenge, is the governance again. So now you not only have to get approval from, I guess, our partners, but then you'll also have consumers. We could require them to prove that they have signed agreements with the original data provider. And then also all of the data sets are structured differently. So even so once again, like it's that image pre-processing. So each of the images might look different. So it's almost guiding the consumers like how to make images from different data sets a bit more similar to work with.
Mhm.
But then also querying that metadata. One interesting thing was like, how can we make it as easy for someone to query data that we added to the data lake, like from partners, which is available for consumers, versus the data that's publicly available? Is there like, how do we make the data points more consistent for querying?
Yeah. So it sounds a bit more complicated than what we deal with Kaggle, right?
Certainly is.
So it sounds like what you guys are talking about is fairly extensive processing and automation to get that data ready to start building models, agree on what schemas are being used, both for the input and the outputs. So yeah, a lot of that sort of negotiation, right? Joe, reflecting on that, where do you see the balance of ML work? Is it more in this data engineering work? Is it more in building the models, training the models, or is it more getting all the labelers to come in and do validation? What's your gut feel on what you're seeing as the balance of work?
Look, I think so. When I started with Datawi, I think our sort of or the general feel within the company was that most of the work sat on the data science side. So in the modeling and the actually building and evaluating models. I think as time went on, we actually got into the nitty gritty of it. We found that the vast majority of the work was actually on the engineering side. So it was prepping the data, aligning data sets, setting up data governance models. Things like that. Like we found that took probably 80% of the total time. And really, once that work's been done, it makes it much easier and a much more streamlined process to run a bunch of sort of parallel experiments with different model architectures and things like that to determine which is the optimal end result. So yeah, the vast majority of the work we found was in engineering that data, prepping it up, cleaning it, and making that data ready for consumption by data scientists.
Yep. In your experience, Joe, I mean, it's just image processing, right? Or is it more data?
On my end, same thing. I think went in, expect to build some models, but then actually, like, okay, where's my data set? And like, oh well,
Yeah.
the DICOMs are stored here. Oh, hold on, what's the DICOM?
Yeah.
Oh, but I just did some images, and then so just like I said, there's a whole big chunk of work to be done before you get to that stage. And indeed, it is once you got the data lined up properly, things get easier actually, and especially lately, a lot of the, I guess, ML engineering is simplified, but I still find the data engineering, each new source of data comes with different set of challenges again. So I don't see that changing rapidly.
Yep. And a lot of the ML process, the optimization, it's not like we just go away and label all this data and then train the model and we're done, right? It's very iterative, right? So that process of it's really important then, isn't it, to track like how we what are the versions of the model we create and how does that change over time? So how important is that provenance component of how it traces to your model? Any labels that are produced, do you have to trace that to the models that are producing it, and what's the versioning requirement on that?
Yeah, I guess this is super important. And coming back to my previous example there, like if you don't know why something was labeled a certain way, it becomes really hard to debug these things. So yeah, if you're doing validation, you just want to see why is, like, if there's mistakes, you want to start looking at the ground truth, and if the ground truth doesn't make sense, where does that come from? How do I trace this back? Should I talk to a labeler that's consistently making the same errors. Maybe my definition is not clear enough. But that's a big one there. But also, I guess, if you want to start reproducing or building some transparency around your models, it often helps to explain exactly how my model was validated and what kind of distribution sets of data did I include in my training validation set.
Yep.
So it really makes it, once again, it's that whole debugging, validation, assurance piece. I think you cannot get that right without being able to trace back what's actually gone into a model, how I guess these test sets have come about.
Yep. And in the previous episodes, we've talked a bit about that sort of validation piece, being able to stratify. So a lot of times that stratification is not at the peripheral, it's actually looking at other linked data we've got, right? So do we have to have capability in the data store for people to pull that information out to separate that as well?
Yeah, so absolutely, like that's integral. So what we found at Datawi was we were sort of building or working to build like a data engine to build iterative data sets to share with consumers. So when a consumer came in and produced a model based on perhaps the original Metavision data or the ECG data sets, we wanted to take that model, generate labels with that model, and then write those labels back to the data set so that those labels can then be shared with future consumers. So obviously, if we're in order to share those labels with consumers, we need to be able to at least estimate the accuracy of those labels and have some sort of metric for tracking our confidence in those values that are produced. So having that data available and that provenance clear within the data store so that it can be queried was fundamental to what we're trying to do. Because again, if we're sharing labels with a consumer, we need to be able to communicate our confidence in those labels, how they were produced, can they be reproduced, and if perhaps the labels were only produced for a subset of the original data and the consumer wanted those labels to be run over a wider set of the input data, then we needed to be able to know where those labels came from so that we could then expand on that and run them over the entire data set.
Yeah, and that's an important point you make, that the data store had to be hierarchical because those earlier sets of labels were often used to drive later sets of labeling tasks, right? Like I think, Stan, you talked about the view classification being quite important for later steps of being able to sort of segment out images. We needed to know what views we're interested in, things like that, right? So that data store is very hierarchical in the way that labels get built upon each other to sort of define the later task selection that the team need to undertake. Yeah, well, I think we might sort of wrap up for today, but again, just want to close on any words of wisdom you'd have for someone starting out, in a bit of a greenfield site. They're starting to build things. What recommendations would you say to them about as they start thinking about how they organize and structure their data and what sort of data store they start building out?
Guess from my end is document early. If you have schemas, write them down. It's one thing to know what all these things mean to one person, but they might not be useful to another. So having these schemas, come up with some sort of data contracts, like what's the data, what data should I expect, and is this ever going to change? Because that'll drive a lot of decisions of how you're gonna come up with your pipelines and how you're going to validate, I guess, data quality as well. And then, just provenance, super important. When I started out, it's often, I'll create a subset, I'll extract some frames from this video, and I'll do some, I'll randomly split a train validation and test set, and then you end up with data leakage, etc. And or then a project becomes more more commercially viable, and then you gotta start building on top of that. And if there's no way of finding out how you actually what data was already seen by the model, it just sets you up for things which are very hard to debug later down the line. So just keeping track of things up front, really important.
And Joe, if you can speak to that, but maybe also what are some of the skill sets that you would recommend to people to have in supporting some of these things that Stan's talked about as well?
Yeah. So look, just to touch on the previous point, I think the big lesson that I learned from my perspective was just to sort of a solid and well-built data model is key. Something that's going to scale well, is going to be easily queryable, and will provide consistent speedy access to those data sets was integral from my perspective. I think we ended up iterating on the data model we used to store some of these data a couple of times, and then that comes with its own challenges then, as Stan's touched on with the versioning. You will then have consumers running off different versions of your data, and that needs to be made clear. And it's not always a simple task let's say that perhaps a small change in the data model can result in much more widespread changes downstream. So really building out a solid data model before you start looking at this would be my piece of advice. In terms of the skill sets, I think just good Python skills is probably the main one. You can't go wrong with some good Python programming. So Docker and building out containers is another key one. As I touched on before, data modeling and sort of understanding how to model and store your data, and obviously the technologies you're using to store and query your data are going to play a big part in how you model your data effectively. So I guess so understanding the infrastructure behind the data stores you're using is pretty fundamental. So most of that is going to be in the cloud these days. So having a good understanding of sort of cloud database technologies and what's available is they're probably the fundamental things I'd recommend.
Yeah, cool. Okay, well, thanks, Joe and Stan. A good chat. We could, it's quite a technical thing to really understand the data, but I think something that's really overlooked by people when they start these tasks. As you said, Joe, you make some easy shortcuts at the start that you come back and you've got a fair technical debt to wear on it later on in terms of keeping the project moving forward. So we could talk a long time for that and get quite down and dirty in the technical area, but I think we've covered a bunch of the high level things today. So thank you for your time today, and I'll keep exploring that data. Thanks.